Hey there, awesome physics students. Let's talk about a situation where mechanical energy is conserved. So what do I mean by mechanical energy? Well, when we listed our different forms of energy over here, there are three: kinetic, gravitational potential, and elastic potential energy that are considered mechanical energy because they only depend on the mechanical configuration, the positions or the speeds of various objects here. So if you have only these three forms of energy involved in the energy conversion, then mechanical energy will be conserved and you can solve the problem similar to what we're doing here. So our scenario is this. You have a large hill and a roller coaster at the top of the hill. The height of the hill is 30 meters. And you have a roller coaster car. The mass of the roller coaster car with the people in it is 250 kilograms. And at the very top, these cars, they get pulled up to the very top with a chain, and then at the top they're going very, very slowly, almost released from rest. But this one is released at an initial velocity of 1 meter per second. And so we want to find the velocity at the bottom of the track here, at the bottom of the 30-meter hill. If we imagine that friction along this path is negligible, that is, it's very small, very little energy will then be converted into thermal energy on the track, and then these are the three forms involved in the conversion. And so mechanical energy will be conserved. Okay, so the idea here is that in the initial energy here, it will be converted into kinetic energy at the bottom. So let's write out our various forms of energy. So the initial position is up here. The forms of energy that it has are gravitational potential energy, that is the mass of the cart times g times the height. And so I'm going to set the 0 point for my gravitational potential energy to be at the ground. You don't have to do this. You could set the 0 point up here and you'll still get the correct answer, but it's just very convenient to do it that way. Okay. So keep in mind, too, that this gravitational potential energy is shared between the mass of the cart and the Earth. It's just because you're bringing the Earth and the cart farther apart by putting it up on top of this hill. But it's mostly, so we typically associate with the cart itself, even though the Earth is involved there, too. All right. We also have kinetic energy for the cart. So that's 1/2 mass of the cart times initial velocity. That's the 1 meter per second squared at the top. And that is converted into the energy at the bottom, which is all kinetic. So it's just 1/2 mv final squared. Okay? And by saying that energy is conserved, we're saying the initial energy is equal to the final energy. That's what this statement means. Energy is conserved. So that when we write this out, mgh plus 1/2 mv initial squared is equal to 1/2 mv final squared. Now keep in mind, with this equation, this says the same thing as one of those energy diagrams where we draw where the different forms go into with the circles and the rectangles. What we're really saying here is that gravitational potential energy and kinetic energy of the cart are converted into kinetic energy of the cart at the end, and none of it is converted into other forms like thermal energy. Okay? All right, so we can actually, we want to solve for this final velocity. Let's take inventory here. First of all, we notice that mass is in every term. So I can divide everything by the mass, and that will go away. So that doesn't actually matter. The other thing is, let's think about which things we know and which we don't. So we know g, that's just a constant. We know the height, that's 30. Half is just a number. We know the initial velocity. We know the half is just a number. So this is the only thing we don't know. So we have one equation, one unknown. We can solve this. Okay, so we want to solve for that. Let's multiply everything by 2 to get rid of the half there. And so this gives us 2gh, and then the 2 multiplied here will get rid of the half here. So I get v initial squared is equal to v final squared. Okay? I want to get that v final by itself, so I need to take the square root of both sides here. And that will give me v final as square root of 2gh plus v initial squared. And if I put the numbers in, I'm just going to put the numbers in with no units just for clarity's sake. Here is 2, and that's 9.8. Height is 30 meters, plus the initial velocity is 1 squared. So when I plugged it in my calculator, I get that equal to approximately 24.3 meters per second. Okay, let's do a sanity check on this to see if this even makes sense. If I convert this into miles per hour, this is going to be about 54 miles per hour. And if you know, various roller coasters will have a maximum speed, a top speed of about 50, 60, maybe 70 miles an hour. So this is actually not very unusual for a roller coaster to have a top speed at the bottom. The other thing we want to think about is what would be the effects if we included friction, if we knew how much energy was lost to friction or the thermal energy that would go into the track because of the friction process. What would be the effect on the speed at the bottom? Well, if some of this gravitational and kinetic energy at the top were converted into thermal energy plus the kinetic energy at the bottom, it means there would be less kinetic energy at the bottom, so the speed at the bottom would be less. So this number, if we included friction, would be lower. So what we've computed is an upper limit to the speed. This is the maximum possible theoretical speed with no friction. If there were friction, this would be less. Okay, so this is how you do one of these situations with mechanical energy. Again, only these three forms are present, so that's why when we can use this framework.